Hello and welcome to Berlin Brains, the joint event series of the Urania and the Charité, in which neuroscientists present themselves and their work. My name is Jochen Müller. I have the pleasure to be your host this evening. And I welcome you to modern neuroscience in the oldest science center of the world. 2022, Berlin Brains is in its 8th season. And this is this year presented by the Einstein Center for Neurosciences, the Excellence Cluster NeuroCure, the Max Delbrück Center for Molecular Medicine in the Helmholtz Association, and the Sonderforschungsbereich or Collaborative Research Center 1315, and last but not least, today, the Bernstein Center for Computational Neurosciences. In Berlin Brains, we present the brain, its cells, the nervous system, the function of those cells in a way that is understandable for everyone. This is the DNA of the Urania, which does so since 130 years. And it's also the aim and the wish of the researchers, because they have a stressful job, but they do this for you, for the people. So during the next 1 hour, roughly, two of them, Elisa Filovich and Polina Arbuzova from the psychology department of the Humboldt-Universität and the Metamotor lab of the Bernstein Center for Computational Neurosciences, will talk about higher brain functions, about metacognition, what it is, how they study it, how they found out, what they found out when they ask, can you raise your left eyebrow? And when they do so, they will talk about much more than what you can do with your facial muscles. But they will not do this in a boring scientific talk. They will not show you a lot of graphs and tables and figures, but they will do that in an understandable and enjoyable way. With both neuroscience and speaking understandably, they stand in a long tradition. As I said, on the one hand, the Urania was founded 130 years ago, 1888 to be exact, and since then we give scientific talks and workshops and events for the people, right, for non-scientists. Also, neuroscience has a long tradition in Berlin. It's among the oldest and biggest research fields in this city. Some famous researchers have worked here, and I will just mention a few. For example, Alexander from Humboldt, the godfather of science in Berlin, in 1797 discovered neuronal activity here in Berlin. In 1848, a person called Émile de Bois-Reymond, we will hear of him today, was the first who recorded currents from neurons here in Berlin. Two of his students, Gustav Theodor Fritsch and Eduard Hitzig, in 1870 worked on functional mapping of the cortex. They discovered the motor cortex here in Berlin. And also here in Berlin, Corbinian Brodmann in 1909 did some histological mapping. He divided the cortex in 52 areas that still carry his name until today. This and a lot more was achieved here in Berlin. And unfortunately, we cannot hear these forefathers speaking about their research, but we and you at home, you can watch today's researchers talk about it. And you can also watch the videos from former Berlin Brains events, because since 2020, we stream them live, we record them on video, and we present them afterwards on the one hand on urania.de, in the Mediathek, on YouTube, and on dasgehirn.info. Like this year's shows, for example, we started in February asking how do genetic changes lead to cognitive abilities. In March, we talked about protein origami and asked how do misfolded proteins damage the brain. Today, the two ladies will talk about their research, and today is also a premiere for us. We do this in English for the first time. Please give us feedback afterwards, how you liked it, how you can do this from home. I will tell in a bit. Still, streaming is good. Coming here live is much better. Oops, we have. So come to the Urania. If you are in Berlin, come here, get in contact. Live, the experience is always much nicer, but you can also get in contact with the speakers. You can ask them, you can really discuss with them. Also afterwards, we have a nice bar here. For example, next month, also in May, two wonderful people will talk about how they take a cold, hard look at how the brain represents temperature. And in June, we will talk about what a two-phase protein called tau does for the brain in health and disease. If you cannot come here, as I said, welcome to all the people watching from home. You can still interact with us. You can also ask questions from home. Just open another tab on your browser. You don't have to install anything. Go on slido.com, SLIDO.com, and enter the hashtag of today, BB0422, Berlin Brains, April 22. BB0422. Then you come to the page of today, you enter your question, and afterwards in the Q&A section, I have this on my tablet, and I will ask the questions to the speakers. Okay, as I said, a lot has been done in the last 200 years in the field of neuroscience. A lot of questions have been answered, but a lot of questions are still unanswered. And today we're even going to talk about or hear about questions that some of the godfathers of neuroscience have said are absolutely impossible to answer. Still, Elisa Filovich and Polina Arbuzova, well, that doesn't stop them from trying. And they will talk about their work. Why together? Because the conceptual motto of this show is junior meets senior. Science is teamwork. It's never done alone. And the first speaker of this event series, usually principal investigator, professor, or group leader like Elisa, she will introduce the field, introduce you to the overall question she will answer with her research group. She wants to answer with her research group. The second speaker today is a PhD student, and she will give more detail about, well, what concretely she does in order to answer the research question that she wants to have a title for afterwards. Taken together, this will take roughly 45 minutes, and then afterwards we will have a Q&A session. For the people in the hall, we still are under some corona constrictions. Finally, I can take my mask off before I go on stage, but for you, please, we are not allowed to give microphones to the audience. So when you want to ask a question, maybe you have seen it, next to the entrance door, there is a microphone stand. So if you have a question, afterwards go up there, and when you talk to the microphone, then please wear your mask. You don't have to wear it when you sit, but when you speak to the microphone, then please wear your masks. Again, for the people at home, slido.com BB0422, this is the hashtag of today. So now let's see who's gonna speak to us today. Elisa Filovich was born and raised in Buenos Aires in Argentina. She studied biology there, received her master, and then moved to London to start her PhD in cognitive sciences. Then she came to Berlin, where she's been since the last 10 years. She started a postdoc at the Max Planck Institute and then changed to the Humboldt-Universität, where she became a junior group leader at the Institute of Psychology. In her group called Meta-Motor Lab, she works on metacognition. Outside the lab, she said she once was proud of being a not too terrible foil fencer, and I love that sentence. Now that she has 2 kids, her hobbies include keeping her hair food-free, at least until noon. But she's looking forward to the time when her kids are old enough to hold a saber, and I would love to see you guys have fencing matches at home. I mean, who wouldn't like to have that? Directly after her PhD student Elisa will talk. Polina. Polina Arbuzova was born and raised in Riga in Latvia. She did a bachelor in neuroscience in Scotland and then moved to Berlin to do her master at the Freie Universität in social, cognitive, and affective neurosciences. She's now in her final year as PhD student at the Berlin School of Mind and Brain of the Humboldt-Universität as a member of Elisa's Meta-Motor Lab at the Bernstein Center for Computational Neurosciences. Apart from that, Polina is passionate about science and open science initiatives, mental health projects for graduate students and early career researchers. And if she's not in the lab, then you can find her at theaters or music scene, in the music scene of Berlin, or on a hike in the beautiful nature of Brandenburg. So please now welcome with a warm applause the first speaker of today, Elisa Filovich.
Okay, thank you, Jochen, for the introduction. And exactly, the title of our talk is Can You Raise Your Left Eyebrow? And perhaps the more scientifically accurate subtitle of our talk is How Much the Brain Knows About How the Body Moves. Before we even get to asking these questions and trying to answer them, I need to give you a little bit of background. So let's start from the beginning. Together with my research group, we study the brain. This is a weird organ. It's pink, it's wet, it's squiggly, and it's squishy. It's first and foremost very complex. It contains, according to some estimates, 86 billion neurons, which is a lot, especially if you consider that those 86 billion neurons have connections between them. But what's most interesting to me about the brain, beyond its complexity, is that it's aware. It has subjective experience. Philosophers like to say that there's something that it is like to have a brain. It feels like something. It doesn't feel like anything to be a stone, and it doesn't feel like anything to be a muscle, and it presumably doesn't feel like anything to be an array of LEDs on the screen of your computer camera. But it feels like something to be a brain, encased inside the body and interacting with the environment through that body. If you think about it, that's really weird. How is it possible? How is it possible that just a careful array of cells of different types, just placed together, give rise to subjective experience, to the experience of red, of pain, of shame, of amazement, and affective touch? All this weird and complex part of our subjective experience just emerges from the brain. This is one of the oldest questions perhaps one of the oldest questions in neuroscience, and it's arguably one of the most difficult ones. It's so difficult, in fact, that, as Jochen just said, some people have argued that it's impossible to answer. For example, in 1880, Émile Dubois-Reymond, who was not far from here, and he was the rector of the same university that Polina and I are working in, said that when it comes to the relationship between the brain and the mind, ignoramos et ignorabimus. That means we do not know, and we will never know. We will just never know how it is that cells give rise to subjective experience. More recently, in 1994, the philosopher David Chalmers, with a lot more nuance, and I think also with a lot more rock and roll, famously coined the term hard problem of consciousness. He split the science of consciousness into two kinds of problems, those that are easy and those that are hard. There's nothing easy about the easy problems. They're just comparatively easy. But the point about them is that they can be solved in principle. We might one day be able to, for example, map every single one of the neurons in the adult brain and map all the connections between them. It's challenging, and it requires technologies that we don't have today, but we might, in principle, one day be able to do that. But he said, even if we were able to do that, and even if we are able to describe every single piece of neuronal activity that happens when people see red, we will still never understand how it is that there's a jump between, so how this jump happens between cellular activity and the experience of red. Okay, but Dubois-Reymond and Chalmers might be right, but we're scientists, and we're interested in subjective experience. We think it happens in the brain, and we just have to try. We have to try to ask the question of how it is possible. And we're interested, in principle, in the complex subjective experiences that we all have in daily life. For example, romantic love. So it would be great if we were able to bring a couple in love to the lab and just get in there and measure their interactions and measure their brains while they are in love. This is interesting, but it's very complicated. It's a very complicated situation to study. So as neuroscientists, what we often do is resort to a much simpler experience in this case, for example, studying visual perception of color. So what we often do in the lab is ask people to come and volunteer to take part in our experiments. We will call them participants, and I will refer to participants throughout this talk. And we show them things on the screen. These things, we call them stimuli because they're very well controlled. We control exactly how long these images appear for, their duration, their contrast, their intensity. And we make sure that we know exactly what we put into a brain, and then we just ask participants to report what they see. We ask for subjective report. We ask people to report their experience. But this, simple as it sounds, is already where the problems start. So imagine I were to ask somebody to tell me what they see there. And then they reply, well, I see red. What can I do with that information? Where can I go with that? I hope this reminds you of being a child and asking yourself, or asking your parents or your family, is the red I see the same red that somebody else sees? This is it's a fascinating question, and it's one where whenever I see a child that asks that question, I jump at them and really try to make them think, because it's a pretty interesting question, and it has to do with the fact that subjective experience is intransferable. We cannot, beyond just reporting and using words to say what we see, we just cannot directly transfer the experience that we see to somebody else. Okay, so just asking people what they see won't work. How about, as scientists, we go one step further and say, well, give me a rating on a continuous scale of how red you see something. This also is associated with lots of problems. Because, well, I don't know. If somebody tells me, yes, it's not very red, or this is very red, how do I know exactly where they put their anchor points? What is very red for somebody? Is it the same for me as for somebody else? And so what neuroscientists have often done is instead use what we call objective measures. We present, for example, 2 different images or 2 different stimuli to a participant and ask them, okay, don't tell me about your subjective experience. Just choose with a button and tell me which one is redder or which one is darker. And we can then usefully quantify whether participants responded correctly or incorrectly. This is nice. It's very well controlled. It has led us to understand, for example, the limits of visual and color perception. But it leaves out the question of subjective experience. We're no longer asking participants to tell us what they see and how they feel. And so then comes the field of metacognition, which is what Polina and I are working in, and in general, the whole team, and with metacognition, what we try to do is unify these 2 sides. So ask, on the one hand, objective questions where we can objectively say whether the answer was correct or incorrect, but also ask people about their subjective experience. Metacognition, we can define it as thinking about thinking. So it's essentially the brain reporting what the brain is also doing. But you can set aside that definition for a moment and bear with me while I try to explain what we do in the lab to measure metacognition. So what we do is first, we show participants, as I said, 2 different stimuli and ask them, in this case, to tell us which one is darker. And then we ask them to tell us, to give their subjective experience of confidence, how sure they are that they gave the correct answer. So here we would get a rating on this particular point of the scale, but we repeat this hundreds and hundreds of times, 300 times, sometimes 400 times for the really daring ones. We might have a participant that looks like this. We have our scale of confidence that goes from I'm guessing, or I was guessing, to I'm very sure. And we start to gather trials. And so on some trials, participants respond incorrectly, but they told us they were guessing, so fair enough. Then they responded correctly and gave a little bit higher confidence. And then 3rd trial, they responded incorrectly again. And then we go on and on and on and repeat this over and over again. And maybe you start already seeing a pattern. So you start to see that this particular participant is able to use their confidence to discriminate correct from incorrect answers. Sometimes they gave us correct answers that are on the low end of the scale, but that's fine, because that was just a lucky guess. They were guessing, and they just happened to tell us correctly which one it was. A participant that behaves like this might look like this. This, for those of you who don't know him, as I didn't, this is Dobby, who in the Harry Potter universe is an underconfident elf. Let's summarize him this way. We might have a different kind of participant who doesn't quite behave this way. Here, this other participant seems to give us very high confident responses, so always consistently reports high confidence, regardless of whether they're correct and incorrect. This other participant might look like that on the other side. So as scientists, what we do is we label these two kinds of behaviors differently. We say that Dobby has a high metacognitive ability that is 1 or close to 1, and that Mr. Trump has a low metacognitive ability of 0 or close to 0. There are a couple of things to note here that we can achieve with this method to study metacognition. One is that we no longer have to trust subjective report blindly. We can take subjective report, we ask participants for the subjective experience, but also quantify whether it was correct or incorrect. So that's to me, the beauty of it. Additionally, this paradigm allows us to separate confidence biases, so a general tendency to rate high confidence or low confidence, and its accuracy. So we might also have a participant that's like Hermione, who in the Harry Potter universe is a very bright, very competent student, and who does have a tendency to rate high confidence, but again, she's able to discriminate with her confidence between correct and incorrect answers. Okay, so now we have a method to measure metacognitive ability. We can, and it has been used, not only to measure visual perception, but also other kinds of perceptual domains. So most of research has focused on vision, but also there are studies on audition, to a lesser extent in touch, olfaction, almost nothing on taste. In fact, in one pretty influential study was done in 2010 by researchers from London, and they tried to find which areas of the brain correlated or had higher gray matter density in those participants who were able, also who had high metacognitive ability. They found that the region within the orbitofrontal cortex, which is basically here, just above your eyes, correlated with participants' metacognitive ability. But in our lab, we said, well, we looked at the research in visual metacognition, and we thought this is fascinating, this is a wonderful, powerful method, but it's neglecting half of the experience that we have, because we're not only experiencing visual and perceptual input. We also are able to introspect. We experience our emotions, and we can report them. We can experience whether we're mind-wandering or on task. Are you listening to me, or are you thinking about the supermarket shopping that you have to do later? We also can report on our motor control. We can report on our motor intentions and the way we've moved our bodies. And we wondered, more generally, whether looking at this side of the screen wouldn't perhaps give us any useful insights about subjective experience that we wouldn't be able to learn from studying perceptual metacognition. In particular, we focus on motor control because we think it's a really interesting instance. If you think about it in daily life, there are many situations in which you do very precise movements, very finely controlled, sometimes very dangerous, like chopping onions. And you don't think about them. In fact, if you were to think about it, you might make motor mistakes. And one thing that I found really fascinating is if I had to teach somebody to move their hands, I would not be able to do it. I would just say, well, take your hand and move it. That's all I can do. This experience and the ability to move our hands seems cognitively impenetrable in a way. So we thought, well, perhaps we don't have good metacognitive access to our movements, but we had to test it in the lab. So that's what we did. And just as the case where I mentioned before, where instead of studying romantic love, we resort to studying visual perception, instead of studying complex and interesting motor behaviors, we take a very simple ball-throwing situation and study metacognitive access to that. So we don't even study people throwing basketballs, but this is just to give you motivation for the questions that we're going to ask. Imagine you're throwing a basketball to reach a net. Will you be able to describe exactly what your body did, even though it might not directly affect the way the ball flew? Or do you only care about the result of your movement? So do you really focus on your body or on the end goal? From our studies, and Polina is going to say something more about this, it looks like we can, in fact, have metacognitive access to the way our body moves. We also asked, okay, forget the body, do we also have metacognitive access to the way that the ball flies, so the direct effect of our actions? That also seems to be the case. And final question was, well, perhaps all this is helped by the outcome of a movement. So if you think about it, the only thing that matters when you throw a basketball is whether the ball went into the net or not. So are we better able to report our movements when we have information about the outcome of what happened with them? Surprisingly, that was not necessarily the case. The answer is more complicated, but we can summarize it this way. Further, we're starting to do data analysis where we're going to try to understand the neural basis for the metacognitive ability and for motor metacognitive ability when we monitor our movements. So where does this all bring us? Let's go back to the hard problem for a moment. This idea that the problem of consciousness is so hard, I think, comes from the fact that we are trying to get to a very complex and very difficult thing, which is subjective experience, and that's difficult to describe, and as I mentioned, intransferable. But what we have been doing with metacognition, if you think about it, is shift the focus of the problem a little bit. And we no longer have this impenetrable construct. We can now ask about subjective experience. We don't have to trust it blindly. We can quantify whether it's correct or not and how precise it is. What we've done, so Polina will give some more details about what we've done there. But what I think this results in is similar to what Anil Seth said a little bit more recently. He gave a very famous TED Talk, perhaps you've seen it. He said, well, fine, the hard problem might be hard, but let's focus on the real problem. For him, the real problem is something different, and he compares it with life. He said a few centuries ago, life was a mystery. We didn't know what life was, we didn't know how it happened, we didn't know what the difference was between life and death. But now, it's really not mysterious anymore. We understand the nuts and bolts, we understand how life happens. And so he thinks that consciousness might be comparable to that. And if we can, for example, manipulate the brain and predict how subjective experience will change depending on which kinds of manipulations we make to the brain, then we will see that the hard problem vanishes in front of our eyes. And I think and I hope that by taking subjective experience, in particular about motor control, and dissecting it into little pieces and understanding which aspects of it we have access to, we are basically trying to tease apart the hard problem to make it a little bit easier. So I will now hand over to Polina, who will try to answer these questions.
So as Elisa said, we study motor metacognition in our lab. And as scientists, we like to study it in a more controlled way. So in fact, instead of studying motor metacognition of arm movements during ball throws, we didn't use basketball because this wouldn't fit in our lab. Instead, we used a simpler game, so-called Skittles Game. It's an old pub game where you have a ball hanging on a rope from a central post, and then you have to swing it around the central post and hit a skittle, so a target that is standing behind it. To make it even more controlled, we did it in a semi-virtual way. So actually, participants were not throwing real balls. They were moving their arm as if they were doing it. We also had a special device that, first of all, allowed us to record the movement they did, but also allowed participants to control the release of the ball, and they saw the corresponding scene on the screen. So when they moved, they saw the ball flying on the screen. So in the experiment, participants first performed the ball throw, and then, after they did it, they saw two trajectories on the screen. One corresponded to the throw they just made, and another one was very similar, but slightly changed. So we made a fake trajectory. And then participants had to choose the one that was actually generated by their movement. So then, after they made this choice, we could also tell whether they did the right or wrong choice. They had to tell us how confident they were in this decision, so how they felt about this. And then, after they've done it a couple of 100 times, we could see how confidence ratings were relating to the accuracy of their responses. So we could, again, put together the objective performance and the subjective ratings, and also quantify it. So when we quantified it, we actually found that participants are indeed relatively good at reporting how well they moved. So they had metacognitive access to their arm movements during a ball throw. Here, it's a graph that shows how metacognitive ability looked for participants in this experiment. We also had different types of trials. So here you can see, for example, first in visual motor version of the task, participants were doing the throw and they also had more visual information about it. Then in the motor case, they had to rely mostly on the motor information. And then we also had a version of the task where participants were not doing anything. It was actually passive. They just watched balls flying on the screen. So it was a visual task. And we also measured metacognitive ability. On top of that, we also compared it to a more classical visual task, like Elisa described before. And then we can see that the mean metacognitive ability measure, that is the thick line in the middle of each column, it was significantly above 0. So if the metacognitive ability were very low, so it would be very close to 0. And if it's very good, then it's closer to 1. So here we see that motor metacognitive ability was comparable to visual metacognitive ability, so pretty good, actually. I guess you're still wondering, what does it have to do with left eyebrow and lifting it? So in fact, we not only did an experiment with arm movements, we also did an experiment with facial movements. And before I tell you how we did it in the lab, I would like you to participate in a small experiment right now, right here. Are you ready? Okay, let's do it. So first, please find a pair. So find someone next to you. Okay? Right, so everyone paired up, or you can do it in groups. Then try lifting your left eyebrow. I will also try. Okay. Okay. Okay, now also tell how well you think you did it, and then tell it to your partner. So share your experiences. How well are you doing it? Can you do it? How high it is? Does your partner agree? Okay. All right. So in our lab, we actually did an experiment where participants were not only lifting their left eyebrows, but were moving their entire face. It was in a much more controlled way, maybe a bit less fun, but we like to make things controlled. So in the experiment in the lab, participants first had to make a facial expression. Then we took a photo of them in this moment. And then we had a series of photos of them making some faces. And then we showed them one by one a photo of their face, and then asked them to do it again. And then we took a photo again. Then we also asked them to rate how well they did it, how confident they were that they did it well. So then, with the help of a computer algorithm that can put landmarks on the face, we could compare these two photos of facial expressions and tell how similar they are. So here, for example, the participant was doing it pretty well, so we can also measure the distance between the landmarks, and we can see that they're pretty much overlapping. But imagine if I was doing this trial differently. So imagine that this was my attempt to recreate this facial expression, and then I rated the confidence again. And then when we look at two trials together, we can see that in the second case, the difference between the landmarks on the face is bigger, so the distance between points is also bigger. And then if I were rating confidence, so in the first case, if I were aware that I was doing well, I would rate it higher. And in the second case, I would perhaps rate it lower if I was knowing what I was doing. And then if I was doing it many, many times, we could also see again how confidence was relating to the distance between the dots on the face. So then for all participants, we could plot it. We could plot confidence against distance between two images. So distance would show how well people are doing. And then if participants had good metacognitive access to their facial movements, we would expect higher confidence when they were doing well, so when the distance between two images was small, and lower confidence when the distance was larger. And if their confidence was not reflecting of what they were doing, and it was all over the place, regardless of the distance between two images, so on average, this relationship would look like a flat line. So in fact, when we looked at the data from this experiment, the results looked closer to a flat line. So apparently, people have relatively poor access to their facial movements. So here it's important to underline that it's not really about whether one can lift their left eyebrow or not. It's really about how they also can report it. So are they aware of this? So how well confidence was reflecting the fact that whether you can lift your left eyebrow or not. So next time you see someone who has perhaps a bit less facial expression than the situation requires, or a bit more facial expression that is perhaps needed in that moment, please don't judge them too quickly. Probably they're just not aware of what their face is doing. When we think about it, it's quite strange that we don't know what our faces are doing, because intuitively we don't feel like it, right? So we kind of have a sense that we do express something with our faces. And one reason why this might be the situation that we saw in the data is we don't get visual feedback about our faces immediately unless we look in the mirror. So normally, when we interact with other people, we might get feedback about the overall expression, the emotion that we want to convey, but we don't get feedback about the way our mouth moved or about how our brows moved. So in last 2 years, we were actually all in a pretty unique situation where we spent quite a lot of time with visual feedback of our faces in all the virtual meetings that we had. So this is, for example, our lab meeting. So this is Metamotor Lab, by the way. And perhaps when you were also looking at your face during the meetings, maybe you also noticed that you never knew that you, for example, I never knew that I sometimes frown when I don't intend to. So we did this experiment before the pandemic. Perhaps if we were to repeat it now, maybe we would have different results, but that's an open question. So I showed you 2 experiments and the ways how we can study motor metacognition. And we have the methods to do that. So where can we go from here? So one way to use it is for educational purposes. So there is some research showing that better metacognitive ability is related to better educational outcomes. So perhaps we can use our knowledge about motor metacognition to improve learning of fine motor skills, like playing an instrument. And if it is useful for learning, perhaps then we can first train metacognition, and there is also research about that. And on top of that, we can also study the and yes, of course, it will be nice to have better metacognition if you want to be competent and confident, as Hermione. And then we can also start to investigate the brain mechanisms behind it. So before I wrap up, I just want to pinpoint a few interesting things about these 2 studies. So in the first study about arm movements, we had a feeling that perhaps participants don't know so much about how they move, so it's very hard to report how we move. But we found that actually, no, participants have good metacognitive ability about their arm movements. And on the other hand, in the experiment with faces, we might have a feeling that we know how we move our faces, but it's actually not true when we look at the data. So this just demonstrates that sometimes our intuitions about ourselves are wrong. And this is what I personally find the most fascinating about this kind of research, that it allows us to find the limits of our intuitive understanding. And the methods that we developed to combine objective performance and subjective ratings are very, very useful for that. So perhaps we still are unable to answer the hard questions of consciousness, but by trying to answer the real problems, to solve the real problems, we for sure can learn a great deal about ourselves. Thank you.
Thank you, Elisa, and thank you, Polina, for this truly interesting talks. Thank you so much. Again, for all the people at home, you can ask questions. I have my tablet here. I will see them when you open your browser and you go on slido.com, SLIDO.com, and you enter the hashtag of today, which is BB0422, Berlin Brains, April 22. Type in the question, I see it here, and I ask them to the speakers. Until you do so, and you please, you can go to the microphone, wear your mask, and ask in the microphone, otherwise the people also from home won't hear that. Until then, I want to ask you a few questions. First of all, again, thank you. That was really, really, really cool. I had to think, especially at your talk, with this facial muscle, I had to think, have you ever done this with actors? Because they are really trained at controlling their facial muscles. And if you ever do this, do you think it would be different?
That's a very, very good question. I think we were thinking about it. We had this idea, I think, at some point. And then I saw that a very recent study showed that actors are indeed better, so they have better metacognitive ability but it was shown in a different task. So it was not about facial movements, but I would expect that, yes, so people who are trained in this, or who are also good at this, perhaps could also have some better metacognitive access.
So I need to get some actress training, because I always feel like when I'm on stage then I'm laughing, and when I look at the videos in here, it's always like, wow, like, because of the light, and it's like, God, I look so grumpy. Yeah?
I can relate to that.
Do you do Zoom differently now?
I definitely catch myself more often in the, yes.
Isn't it also disturbing or distracting?
Yeah, I try to turn off my self-view, but it's also difficult because you don't know how other people see you.
Okay. What about people playing poker? This typical poker face, right? They kind of, what do they do? Do they disrupt the connection between emotion and facial muscles, or what is it?
Good question. I really don't know. I think the answer is I don't know, but what I can say is our research would not be able to answer that. We can only answer whether people know that they have a poker face or not.
Ah, okay. When you look at the future, right? You presented what you focus on here, and you're still quite at the beginning of your career. When you retire, what would be your dream? What would be the goal that you said, until then I want to answer that?
If I'm honest, I don't think I have one of those. I think I'm happy just being able to ask the question. I don't necessarily want a concrete answer. It's just fun to think of possible ways to ask it. Right. And that's enough for me. And I also read what other people are doing.
And let people do things. Really, do you really do this hundreds of times?
Yeah.
So how long do the people sit there and do this again and again?
For sometimes 2 hours, yes. We have to give a lot of chocolate and candies to keep them motivated.
I wanted to say that, please give them a lot of chocolate. Goodness. And then you showed us this cool fMRI picture of Fleming. I asked myself when I saw this, that now it goes more into consciousness, but has it ever been done to record people while they're asleep, and then when they are waking up, see what changes, and then you should see on the picture, well, that's what switches on, that's consciousness, right? No?
Yeah. I don't want to hand wave. I don't want to lie here. It's on record. I'm sure it has been done. I think so. The problem is that changes in the brain are there. So you get a lot of changes in the brain when you wake up. Mm-hmm. Your brain connects to your body. You can move it again. You become aware of your surroundings. You see. You hear. So all of that is activity that is. It's what people say is that it's not the neural correlates of consciousness. It's not the core that really differs between, that gives the difference between conscious and unconscious processing.
Okay, oops, sorry, I did something with my tablet. I didn't even know that this was possible. Goodness, I divided my screen and now I can see it. Anyway, sorry, technical problems. Also, sometimes we speak of, especially in sci-fi or when it comes to drugs, of higher consciousness. Do you think something like this exists, and what would it be? Or maybe, I don't know, maybe it's a stupid question, but I just read a book from, oh goodness, called The Light. Has anybody read it? What's the author's name? Yeah, it's about the 60s, where they, Timothy Leary, this person from Harvard, and in the end they were just doing a lot of drugs, but they tried to investigate higher consciousness. T.C. Boyle, thank you, exactly. Yeah. So
I was also reading and I was thinking about that question today. I was wondering if somebody would ask. And I was reading about this in Anil Seth's book that's pretty recent that came out. He mentions this. So he took acid and describes his experience. That's one part of the book. I don't know if I would call it heightened conscious experience. It's just a different one. What I think is really fascinating about that is that you change the chemistry of the brain and the world changes.
Yeah.
So the world as we see it depends on the chemistry of the brain. And that's, I think, really cool. And that's a real cool concept. And it would be, I've never taken drugs, so I don't know how it would be, but I think it would be great to experience this in first person, to say, to really have this experience and very clear notion that, well, it's just the arbitrary chemistry of my brain. I don't know if it's high, it's a conscious experience like anything else, just more bizarre.
Yeah. I mean, this concept is the basis of psychopharmacology, right? When you suffer from a depression, and then you take a pill, the pill works on your body, and your mind state changes.
Yeah.
So obviously, it's all related to chemistry.
But that doesn't generally change perception and your subjective experience as such. So you don't see pink unicorns flying and clouds turning.
But you see the world differently, right?
Yeah, exactly. Just not shockingly so. But yeah.
Other questions from the audience? Yes, please.
I've got a line up here. Does that work?
Yes.
Okay. Yeah, thanks for the great talk. I was curious, you mentioned at some point that we can't tell people how to move their hand, and you show that we might not always have good insight about our movements. So I'm curious if you think this has an impact on how we should teach people to do movements, or if you would teach your children to fence differently, knowing about this, or musical instruments or sports, things like that.
So the motor learning literature tells us that actually it's more helpful to concentrate on the external world, so the changes in the external world. When you're playing a music instrument, you can concentrate on the sound. I guess that works when there is something out there in the world, so some kind of perceptual feedback that follows with that. But I guess that might be different for something that is intrinsically motor and you don't get that much feedback. Like, I don't know, maybe if you want to teach someone to move their left eyebrow, maybe then, without looking in the mirror, maybe then you would have to concentrate on something else and not on the external cues.
Oh, thank you.
Thank you.
If I can add to that?
Yes.
Yeah. I think I don't know how useful it would be. So I don't think, I think the motor literature has done a great job at describing and finding out best ways to, or is doing at the current time, best ways to learn. So I don't think we have much to say about that. It's just interesting. I think it's I just wonder. And I'm fortunately paid to just ask what I wonder.
Next question. Yes, please.
Yeah.
Thanks for the presentation. So my question is, you described two different motor tasks. One of them we have good metacognition and the other one not. Do you know why is it the case? Why we do better in that task, not the other? And is it solely dependent on the feedback, on how much feedback we get? Or are there other factors? And based on that, can we predict if a different motor task will be one with a good metacognition or not? Let's say how they move their feet or was something else.
Good question. So I would say, so immediately I would say that perhaps it is something to do with feedback, but to really confirm this, we would have to have another experiment. So one thing that we have to, I guess, to say that we are really at the very, very beginning of studying motor metacognition. So perhaps if we can somehow manipulate feedback, then we can also see if that's really the feedback. Plus, one idea that I had about it is that maybe with facial expressions, for example, maybe there is some sort of critical period where you have to get this visual feedback so that you learn these kind of contingencies between what you do and what you see, like when we move our arms, so normally we see how we move them. So yeah, maybe with the Zoom example, so maybe it's too late for us to learn how we move our faces while watching in the Zoom. Yeah, Elisa.
No,
do you
I
have-
think that was great.
Thank you for the question.
I have another question. And I once heard a talk about choking under pressure, right? When the example was this football game where Germany won over Brazil 7.0, and this professional, super great soccer or football team all of a sudden didn't hit the ball. I mean, right? And the term is choking under pressure, and the theory is that they focus too much on what they learned for years to do without thinking. They concentrate too much on it, and then so is that like metacognition switched on?
Yeah, I think so. So if you're as Polina said, as what we know from music performance and sports is that it's better to focus not on the actual movements but on the result of that.
Yeah.
So yeah, it's possible that they were nervous, and for some reason that said, well, I don't know what happened in their minds, but yeah, that's the interesting thing. So I think, or intuitively, if you have so when you turn metacognition on when you're looking at, so I don't know if you can turn metacognition on, but a visual task that you do with metacognitive monitoring, you would expect to do that better.
Yeah.
With full attention, you focus on what you're seeing and think about your confidence, etc. That might not be the case for motor control. And that's why we thought perhaps there's something interesting here in motor control that it's worth studying.
This also brings me back to the difference between the metacognition of the arm movement and the facial movement, because my arm I see, right?
Yeah.
But I mean, all my life I move my facial muscles without visual feedback, and maybe I can raise my left eyebrow when I don't think about it, but when I think about it, it doesn't.
It's
work.
possible.
Yeah.
Yeah.
Honey, please.
Hi, first of all, thanks for the presentation. I have two questions, but the first one is more short, so I hope it's okay.
Sure.
So the first question is, when we train a skill, most of the time we get better over time. And then I was wondering, did you maybe also measure how the metacognitive ability developed with like more training, if it improved or if it got worse?
We actually didn't do that, but that's a very good idea. So here in our experiments, actually one important point that I didn't mention is that we tried to make this task equally hard for all participants. Of course, we all vary in our motor skills, so we tried to do this task more difficult for those for whom it was easy and easier for those for whom it was too hard. So then when we equalize this performance in the objective task, we can really highlight the differences in the metacognitive performance. But that's a very good question. One study that I know actually looked at motor learning with kind of drawing tasks. So participants had to draw a certain shape within certain borders. And they looked at that there was a difference in the kind of speed of development. So I don't remember right now which one was growing faster, unfortunately, but basically the motor learning, so improvement in motor skill was changing with a different speed as the confidence in this task was changing. So that's one thing that I can tell about it.
Yeah. Good.
Okay. And the second question is a bit related to it. So I was thinking a lot about reinforcement learning during your talk, and I was always trying to, if I were to like model the human learning process like a reinforcement learning algorithm, to like see how you could map the phenomenons. So I was just wondering if you have maybe thoughts about which part, like, could you imagine interesting phenomenons if you like try to map these two ideas? So I was, for example, thinking if you ask them about their confidence, this would kind of like be a question about how nicely is your loss function working, basically.
I mean, I can try to answer that. I've never thought about the connection between those two, and I don't think maybe somebody in the team can jump up and, Marika, you probably have some good ideas. But I don't think I remember reading any paper connecting the two explicitly. The thing about reinforcement learning is that, I mean, we often in our experiments we don't give feedback about performance. People don't know whether they did correctly or not, and they don't know. Sorry. Now I do remember one paper. Let me finish the idea. They don't know whether they've done correctly or not, and they also don't know whether their confidence was accurately calibrated, so to speak. There is one paper where they looked at the difference in prediction and difference in confidence. I need to bring it. I won't be able to answer very well now. But I think the short answer is I haven't seen any research on that specifically. And with our current experimental paradigms, we can't really answer that.
Okay, thank you.
Yeah.
I have something to add. So there's also one study actually by our colleagues from Charité, so Matthias Guggenmoos, where they looked at confidence. It's slightly different, so it's not combining with reinforcement learning, but they looked at confidence signal as a kind of intrinsic reward signal. So in the absence of any external feedback, so if no one tells you whether you're doing good or not, so this kind of confidence might serve as an internal reward for learning without feedback. And they, I think, even showed that the neural basis is also somewhat overlapping. So that's one thing.
Thanks.
Thank you.
Cool, thank you.
Please.
Yeah, thank you for the lecture. I was wondering if you looked if there were any differences between the genders. Yeah.
Can I try? We actually didn't look at the gender differences, so we didn't have any specific hypothesis about this. And I'm not sure whether our sample sizes would also allow us to make any big claims about it. But one consistent difference in general in confidence behavior, let's say. So it's not really about matching confidence with accuracy, but confidence overall, together with this kind of range being lower or higher. There are certain consistent patterns between females and males, and you can guess in what direction it goes. Then there are also certain patterns with age, right? So, yeah.
Okay.
That's the only thing. I don't know any research about or any results about the combination of confidence and accuracy. So even though probably we are all equally competent, the confidence bias exists, and it's a very, very robust effect, actually.
Thank you. I have another question, and maybe this is more, not so much scientific, but more, tell me what you think. You said in the beginning very nicely the picture that the brain feels like being something, right? What do you think? Do animals, or does a sponge? I mean, is there an all or none, or is there a gradual?
There's a very long question to that answer. So one is, so first I don't know. Let's start with metacognition. There's research, research on metacognition in animals. In monkeys, you can show that they can do a task that you can say it's opting out. So when they are uncertain, they opt out from so essentially you can the task could be something like if you show them a picture and they have to choose whether it goes to the right or to the left, and if they're certain of A, or to the right, they go to the right. If they're certain of left, they go to the left. And if they don't know, then they don't waste any time and go to the next one. Monkeys probably have subjective experience. You can do something similar with rats. And there, I don't know. You can do something similar with mice. And with mice, you can do a slightly different task where it's a time wagering task. So instead of, so you go to the right or to the left, but you can also, and then they have to wait for a reward, but the reward comes at a variable time. So it's not clear if it's going to take 1 second or 8 seconds. The longer the mouse waits for that reward, the more confident they probably are, right? Because then they're there. Yes, give me my reward. I'm sure it was right. But mice, do they really have subjective experience? Do they really experience confidence? And you can do something similar with bees, with honeybees. There's a PNAS paper showing that. It's probably with some experimental flaws, but bees, I don't think they have any subjective experience. So it's a little bit difficult to really answer that question properly. Then that's one part of the answer. The other part of the answer is that there's one theory of consciousness called information integration theory. Maybe you've heard about it. It's by Giulio Tononi. It's a controversial theory. A lot of people have criticized it on the basis that it's not really scientific and not really testable because it requires measuring something that's unmeasurable. But the idea is that the more complex a system is, the more conscious it is. Consciousness is a continuous measure.
Yeah.
So taken to the extreme, this leads to something called panpsychism, which means that everything in the universe has some level of consciousness. Now, the problem is, if everything is conscious, then consciousness is no longer an interesting concept. I want to know where the interesting cutoff is, because then it doesn't matter. It's probably graded to some extent. It's just very difficult to know where the cutoff is. And maybe just one last comment. There's been a couple of papers or a few people in the field that are a little bit more concerned now with experiments in animals. They say, as consciousness researchers, we have to take things a little bit more seriously and stop experimenting with animals. Okay. I personally don't know where I stand there. But it's interesting scientific question.
Absolutely. One more question from the audience.
Hi. Thank you for the talk. Really interesting. I was just wondering how much of a trademark metacognitive ability is. Like when I perform two completely different tasks on completely different stimuli, will my metacognitive ability in these two tasks match? And if so, I think it does. Does this say anything about me as a person? Like, is it related to personality? And in the extreme case, could you even predict metacognitive abilities from personality?
I can try to answer the first half of the question. So what you described is essentially what we call domain generality or domain specificity question. That means if a certain feature is domain general, wherever we test it, vision, motor, memory, you name it, people who have high metacognitive ability in one thing would also have high metacognitive ability in the other one. And then domain specificity idea is that if you have, let's say, good metacognitive ability in memory, it doesn't mean that you have good metacognitive ability in visual perception. And so far, the evidence is quite mixed. At the same time, I think the scales are tipping towards the generality generality idea. Perhaps, as it's often in science, it's probably not binary, so it's not so black and white. So perhaps some parts of metacognitive ability are more domain specific, and some parts are more domain general, and that's actually, I guess, more interesting question now. So what actually makes some parts? So what are the common parts and what are the dissimilar parts? And coming to the second part of the question, the only thing that I know about the personality traits and metacognitive ability is that there is some research about some kind of traits that are related to some clinical conditions. So the study was done not in clinical populations, but in general populations, but still you can say that someone scores a bit higher, for example, in anxiety score, still under threshold, but the kind of some tendency. And there were some relationships found, for example, more depressive, anxious dimension was related to higher metacognitive ability, and what was I guess a more compulsive traits were related to lower metacognitive ability. Yeah, but other than that, do you know any studies on personality?
I can think of the political extremism result.
Yes, yeah.
It's a tiny, tiny effect, one should say.
Yeah, maybe you can...
Yeah, so there's a paper a few years ago showing, I don't know where you are, there, that people in the extremes of the political spectrum, both left and right, had lower metacognitive ability in a completely unrelated visual task. One should say was a tiny difference. So,
tiny.
Yeah, not to be taken very with a, so who knows.
Are there any more questions from the audience? Dare to ask now. They are here, they wait for you, and they're happy to answer them. If not now, maybe we can still meet afterwards at the bar and discuss more about this super fascinating topic. I have one last question. Maybe that is, well, there are no stupid questions, right? Is routine the opposite of conscious?
I mean, I don't know. I would say one classical example is when you drive. You're driving a car and you're not thinking about it. So there, your metacognitive thoughts are somewhere else, not on the driving. So in that sense, maybe when you're doing something mindlessly, I think so. What I think maybe is more interesting is the state of flow. State of flow is this state where a task is just challenging enough. It's not so easy that it's boring, but it's not so hard that it's too difficult. So you're in it, completely in it. Yeah. I don't know whether. So it's not routine, but I don't know what metacognition has to do with that. I just think there's something interesting there.
Okay. Well, we will keep on talking afterwards. I just want to ask you. I want to thank you for being here. I want the people at home. Thank you for watching us. See you again here on May 25th, when Jean-Sébastien Joanneau and Clarissa Whitmire from the Collaborative Research Center 1315 will focus on questions like how the brain transforms neural representation into experience when they take a cold, hard look at how the brain represents temperature. They also tell us what this tells us about perception in general and what this means for all of us. So be prepared, come here at May 25th. Thanks for watching. See you soon in Berlin Brains. And last but not least, I want to thank you for being here, people from home for watching, the team from the Urania. Please give a warm applause to Henning, Felix, John, Julian, Sebastian, and Margaret Franke for paying for this. Thanks, you guys. See you soon. My name is Jochen Müller. Thank you.
Thank you for the opportunity.